Good afternoon, everyone. My name is Jeon from Sungkyunkwan University. And today I'm going to introduce our paper. Our research explores the possibility of AWUPF, an NVMe feature for shifting the atomic line support to the SSD. Let's begin with a brief overview of how SSD handles lines. As you may know, NAND flash memory in SSD does not support direct overwrites. Instead, flash translation layer manages to logical to physical mapping of data. When a write operation occurs on the host side, the data is written to a new physical location in NAND flash. If an overwrite operation is issued, the new data is stored elsewhere. To ensure accessibility, the FTL table must be updated with the new mapping information. Since the mapping table update is crucial for accessing new data, it must be atomic at the mapping unit level to maintain data consistency. Due to this mechanism, SSD inherently provide atomicity. To formalize this behavior, the NVMe standard introduced a feature called AWUPF, which defines the smallest write unit that SSD must guarantee as atomic. Through our analysis, we found that most SSD provide a 4 kilobyte AWUPF. This leads to an important question. Do we still need double writes for journaling? As you know, file system and database rely on journaling or write-ahead logging to prevent partial update. Instead of writing changes directly to storage, updates are first logged in a journal area and later applied to the main storage through a checkpoint operation. However, this approach introduces significant performance overhead due to the double write process. But what if we could leverage AWUPF instead of traditional journaling? Since AWUPF already guarantees atomicity, we could eliminate the need for double writes, significantly reducing overhead and potentially improving performance. Now let's take a look at how previous studies have tackled this problem. Some approaches have modified SSFTL to enable transactional writes, while others have explored offloading host-side journaling to SSD. However, while this study leverages the atomicity characteristic of SSD, they all require modification at the SSD level. But as mentioned earlier, SSD already provides native atomic line support through AWUPF. If a transaction fits within a single page, we can leverage the SSD atomic line capability to guarantee atomicity. Rather than modifying the SSD itself, our approach aims to reduce journaling overhead by utilizing an existing SSD feature, AWUPF. But this leads to another key question. Which system can efficiently update metadata with a single atomic line command? Based on this criterion, we selected log-structured RAID as our case study. Unlike conventional RAID, log RAID follows an append-only write strategy. Due to its out-of-place update method, RAID metadata, which maps the location of RAID user data, must be updated with each write operation. For example, let's say data A, B, C, and D are already stored and their locations are recorded in the mapping table. If your B is updated to B prime, log RAID writes B prime to the next available location on SSD 0 instead of overwriting the existing B. Since the location of B has changed, the mapping table must also be updated accordingly, like this. But what happens if a crash occurs during this update? It could lead to a corrupted mapping table, potentially causing data inconsistency in RAID user data. If the RAID metadata update is only partially completed, the system might reference outdated or incorrect location. To prevent this, RAID metadata updates must be atomic. To ensure atomicity, log RAID employs journaling for RAID metadata, allowing to recover correctly in case of a crash. However, journaling introduces a significant performance overhead. When journaling is disabled, metadata updates are handled in memory and only periodically flushed to storage. In this case, the performance difference between sequential and randomized remains minimal thanks to low-grade append-only write scheme. However, when journal is enabled, the performance overhead increased dramatically by up to 25 times. This impact is particularly severe for small random line. The reason is that during a checkpoint, random line updates multiple metadata pages, significantly increasing the number of metadata page writes. As a result, this leads to a much higher performance cost, making journaling a major bottleneck for low-grade. For our study, we used Poseidon OS as our target low-grade system. This is an open-source low-grade system built by Samsung. The Poseidon OS server connects to the initiator via NVMe OF. When one or more block devices are set up on the initiator, they get connected to multiple NVMe SSD in the Poseidon OS server. In this setup, RAID user data is managed as low-grade 5 or low-grade 6, while RAID metadata is handled as RAID 10. Let me briefly introduce the metadata structure of Poseidon OS. In Poseidon OS, data is written sequentially in log-structured manner. Let's go through an example to understand how this works. When data A is written, it is first stored in virtual stripe, which is allocated in memory, and then written to logical stripe, which represents the actual storage space used in SSD. At this point, to map the virtual stripe to the logical stripe, Poseidon OS manages a stripe map. Next, the VSMap update is committed to journal area. After this, the in-memory VSMap is updated accordingly. Here, the VSMap refers to the mapping of both RAID user data and RAID metadata based on the host address. Each entry in the VSMap contains a VS ID, which means virtual stripe ID, and an offset. Since each virtual stripe is directly mapped to the logical stripe, knowing the VS ID and the offset within the stripe allows us to determine the exact physical location of the data on the SSD. The same process is followed for data B and C. Finally, when the journal area becomes full, a checkpoint is triggered. At this point, since we have updated 3 metadata pages, referred to as M pages, these M pages are checkpointed and written to the metadata area to ensure consistency and durability. In Poseidon OS, one M page is equal to AWUPF, allowing us to leverage AWUPF to ensure atomicity while simultaneously reducing double write. Let's look at an example. If you write A updates only one M page, it can be directly written to storage, bypassing journaling. In contrast, if you write operation B update 2 M pages, it must be committed and later checkpointed to maintain consistency. However, if your subsequent write operation C updates only one M page, it can also be directly written, potentially including a portion of A's metadata. As a result, previously all 3 M pages required double write due to journaling, but with our approach, only one M page requires a double write. This significantly reduces journaling overhead and improves write performance by minimizing unnecessary double writes. While AWUPF enables direct write to metadata, applying both direct write and journaling to the same M page can lead to consistency issue. The figure below illustrates how the VSMap in memory and storage is updated during a write operation. When write A modifies M page 0 and M page 1 in memory, to maintain consistency, it must be fully committed before any further updates take place. However, if you write B, update the VSMap in memory before write A committed, it directly writes M page 1, including A1. As a result, a portion of write A metadata is stored in SSD prematurely. Now, if a crash occurs at this moment, M-page 1 is stored, but M-page 0 is lost. Since write A was never fully committed, this results in an inconsistent state because write A's data was only partially updated. To ensure consistency, the base map in memory should only be updated after a commit is complete. First, write A is successfully committed. Only after this, the base map in memory is updated. Now, when write B arrives, it can safely write M-page 1 to storage. Since A1 has already been committed, if a crash occurs, in this scenario, recovery is straightforward. M-page 1 already contains both A1 and B, ensuring their persistence. A0 can be restored from the commit log, maintaining atomicity and preventing data corruption. The second issue arises in the following scenario. After write A and write B are complete, write C overwrites the same location as write A. As a result, the base map in memory is updated with write C's latest information and then directly returned to the storage. However, if a crash occurs, at this moment, a critical issue emerges because the system restores the write A or the data from the commit log, effectively overwriting the latest update. Write C information is lost during recovery. This leads to data inconsistency as the most recent write operation is undone by outdated commit log. To address this issue, we introduced a version number for each M-page and implemented the version every time a direct write or commit occurs. This ensures that higher version always represents the most up-to-date M-page, preventing outdated data from being restored during recovery. When a write operation requiring a commit arrives, the M-page version is incremented by 1, and the commit log is recorded with the updated version information. After write A is committed and the base map is updated, write B arrives, the version is incremented again, and direct write is performed. Later, when write C modifies the base map in memory, the version is incremented once more, followed by another direct write. If a crash occurs, the recovery process proceeds as follows. The system compares the version in the commit log with the current version of each corresponding M-page. If the commit log version is smaller, no recovery is needed because the M-page already contains a newer version. In this case, since the commit log version of A0 is not greater than the current version of M-page 0. Similarly, the commit log version of A1 is not greater than the current version of M-page 1. Since all versions are properly managed, no rollback or recovery is required, ensuring consistency and preventing data loss. We implemented our approach in Poseidon OS, and we configured the experimental environment as follows. We tested 3 configurations. Journal used the default Poseidon OS journaling option. Our approach selectively applies journaling or direct write based on the number of updated M-pages. Direct always writes modified M-page directly without ensuring data consistency. First, we compare the performance of our approach with the conventional journaling technique using the same number of reactors. Poseidon OS utilized the Storage Performance Development Kit, a user-level storage I/O framework, to efficiently manage I/O operation to SSD. The reactors are split into metadata reactors, which handle metadata journaling and checkpointing, and user data reactor, which handle user data storage. The performance of journal remains constant in random line workloads, even as the number of metadata reactors increase. This is because checkpoint overhead becomes the dominant bottleneck. limiting the performance improvement from additional reactor. In contrast, our approach improves performance by 3.3 times. Increasing the number of metadata reactor leads to better performance scaling, unlike the journaled approach. Since only one M page is updated with 4 kilobyte writes, Direct shows the same result as our approach. However, in sequential write workloads, both Direct and our approach experience performance degradation. Once the number of reactors exceeds 8, this decline is caused by condension to M-page access, where multiple reactors compete for the same metadata pages, leading to increased latency and reduced efficiency. This is based on a 1 megabyte request size. Since journaled behave more like sequential write, its performance in random write workload is similar to sequential write performance. However, our approach still outperforms journaled by an average of 20%. Additionally, all three methods show saturated performance starting from 6 metadata reactors. At this point, increasing the number of metadata reactors no longer improves performance, as the system becomes bottlenecked by contention in metadata access. To assess the impact of write side, we tested performance across different sites using FIO. Sequential write performance is similar across all three configurations. In random write workloads, our approach achieves up to 3.6 times higher performance. As writes become more sequential, checkpoint overhead decreases, bringing our approach closer to Direct at 2 megabyte write size. We evaluate benchmark workloads where our approach offers advantage. BAML dominant by small random lines show up to 14% improvement at 32 threads. In OLTP, DB writer issues small asynchronous random line. Our approach achieves up to 73% improvement at 32 threads. Significant performance improvement was observed in random dominant workloads. AWUPF has traditionally been viewed as an intrinsic asset feature. However, this study demonstrates its potential for offloading hot-side data consistency management to SSD. By leveraging AWUPF for low-grade metadata update, we achieve significant performance improvement by reducing journaling overhead and minimizing redundant writes. We believe this approach can be further extended if other system architectures are redesigned to align with the AWUPF size. Thank you for listening.